Hi students, we see rotating bodies all around us. Bodies which keep moving like this. But we haven't learnt about this kind of motion called rotational motion up till now. So we will learn about rotational motion in this chapter. We will learn about a special term called torque. We will learn about a special term called angular momentum. We will learn about many parameters and variables related to the rotation of a body in this chapter. We are even going to learn about pulleys with mass. So let's proceed and learn about rotation. Rotation 1, pure rotation. Now first of all, let us understand the difference between the motion that we've studied till now, in the previous chapters, and the new kind of motion, rotational motion, that we are going to study in this chapter. The motion that we've studied till now is translational motion. In translational motion, the center of mass of a body keeps moving on and on. Like this. This block here is undergoing translational motion. On the other hand, in rotational motion, a body rotates around a certain axis. So for example, this circular disc that you see on your screen is rotating about its center of mass here. Isn't it? So basically, when any body undergoes circular motion about any given axis, then we say that the motion is rotational motion. Understood? This axis may be the center of mass of the body, or it may not be the center of mass of the body. You can even say that rotational motion with infinite radius of rotation is actually translational motion. Isn't it? If a body is rotating about an axis and the radius of rotation, the radius of the circle in which the body is rotating, is infinite, in that case the body will just keep on going straight and straight, and the body will undergo translational motion. So we will study rotational motion in this chapter, the motion in which a body revolves around an axis. Now the first important concept required to be studied before we study rotational motion is moment of inertia. Moment of inertia is a property related to the mass of a body that tells us how easy or difficult it is to rotate a body. If a body A can be rotated with less effort, and if B needs a lot of effort to rotate, then B is said to have a greater moment of inertia compared to A. Understood? So basically, moment of inertia represents the resistance of a body to rotation. If a body can be easily rotated with less effort, it has less moment of inertia. If it is very difficult to rotate a body, in that case the body has greater moment of inertia. Understood? So this is what moment of inertia represents, the tendency of a body to not rotate. So how do we calculate this moment of inertia? First of all, let's learn how to calculate the moment of inertia of a particle around a given axis. You see, moment of inertia is always defined about a fixed axis. In fact, in rotation, everything is defined about a fixed axis of rotation. So let us try to calculate the moment of inertia of this particle of mass m about this dotted line, this axis shown. This is the axis. So if this particle m is made to rotate around this axis such that its distance from the axis at any instant is r, then the moment of inertia of the particle will be I equal to mr square. I is the symbol of moment of inertia and mr square is the magnitude of moment of inertia. Moment of inertia is not a vector quantity, so it does not have any direction. So the moment of inertia of a single particle around a fixed axis that is at a distance r from it is mr square. This is something you must remember. If you have many particles rotating about the same axis, then the net moment of inertia of the system is the sum of the individual moments of inertia. So the net moment of inertia of this system, consisting of three particles m, m1 and m2, is m1r1 square plus m2r2 square plus mr square. Understood? And this moment of inertia represents the net resistance, offered by this system to rotation. Understood? So moment of inertia can be added. In fact, if there are n particles, and the distance of one particle from the axis of rotation is r1, the distance of another particle from the axis of rotation is r2, and so on, then the net moment of inertia of the system is sigma mr square. Understood? So you add the moment of inertia about the axis for all the particles to obtain the net moment of inertia about a single axis for all the particles. Now this was about the moment of inertia of particles. But what about the moment of inertia of rigid bodies? Say the moment of inertia of a square plate or the moment of inertia of a solid sphere. If we rotate these bodies about a certain axis, what will be the resistance these bodies offer to rotation? The moment of inertia of a rigid body is basically the sum of the moments of inertia of all the tiny particles that make up that body, isn't it? After all, we just learned that if there are 10 particles, then the moment of inertia of the 10 particle system is the sum of the moment of inertia of each particle. Therefore, the moment of inertia of, say, a solid sphere will be the sum of the moment of inertia of each particle that is a part of that solid sphere. Take a look at this ring, for example. Let's try to calculate the moment of inertia of this ring about its center of mass axis. You can see that the center of mass of the ring is at its center. We have drawn an axis perpendicular to the plane of the ring, this black dotted line, and we want to calculate the moment of inertia of the ring about this axis. What do? So the ring is basically rotating like this. The axis right now is perpendicular to the computer screen. Understood? It's facing towards you. So did you understand, in which plane the ring is rotating? The ring is rotating in the plane of the computer screen, and the axis of rotation is perpendicular to the ring. So what will be the moment of inertia? If you consider a small element dm on the ring, an element means a very, very tiny portion of the ring, an infinitesimally small portion of the ring. In that case, you can add up the moment of inertia of each of these tiny portions of the ring to get the total moment of inertia of the ring about the central axis, isn't it? So we consider this element of mass dm, very, very small mass on the ring, and we try to calculate its moment of inertia. Then we try to integrate the moment of inertia of all such elements to get the total moment of inertia of the ring about the central axis. The moment of inertia of the element is clearly dm into r square, where r is the radius of the ring. This is because the distance of the element from the center of the ring is r, and the moment of inertia of a particle that is at a distance r from the axis is m into r square. So the moment of inertia of the ring is clearly integral dm into r square. Now r is constant, and integral dm basically represents the total mass of the ring, isn't it? After all, if you add up the mass of all these elements, you get m, capital M, the total mass of the ring. Therefore, the moment of inertia of the ring comes out to be I equal to mr square. You must remember that the moment of inertia of a ring about an axis that is perpendicular to the plane of the ring and that passes through the center of mass of the ring is I equal to mr square. What about a disk?